Welcome to the lecture on vibration analysis procedure. So, what is vibration analysis procedure? Here vibration analysis procedure means we are going to do the discuss the mathematical procedure. Here the contents is that we have a physical system and how to do the vibration analysis of that system. What are the steps for the vibration analysis? Then some basic elements of a mechanical system like stiffness or spring, damper and mass will be discussed. So, here we have a physical system and this physical system may undergo vibration under certain external force. So, that physical system how we will analyze? So, here analysis means mathematically. So, how we will model that system, how we will write the equations, how we will solve that mathematics, and based on the solution how we will correlate with the physical system. So, here usually we have discrete system. The mechanical systems, they are two types, discrete and continuous. So, here we are dealing with discrete system, means we are going to divide or represent the system in terms of the three basic elements, that is mass, stiffness and damping, and we will follow certain steps that are for the vibration analysis procedure. So, here first we will make the mathematical model, and if we have a physical system, how we will develop a mathematical model? Of course, mathematical model will be in form of some mathematical equations, some differential equations, and those differential equations will need some solution. So, what are the methods to solve these equations? And we will get the solution. Then these results how we will interpret, how we will correlate with the physical system, what are the property that we want to know, we want to know the response of the system. Okay. So, here are the 4 steps, basic steps. They are mathematical modeling, then derivation of the governing equations or differential equations, then the solution of the equations, and then interpretation of the results. So, mathematical modeling. So, our physical system are usually very complex and we want to represent it in terms of mathematics. It means we have to follow certain assumptions, we have to take out the features that are important, not all the features, but only the features that are more important based on our objective of the study of that system. What is the purpose of studying that system? What is the particular objective? What do we want? For example, if a bike is moving on a road, we want to know the characteristic on a normal road, what is the vibrations coming, we want to know when it is on the bump, what is the response of the system. So, means what is the objective? So, based on this objective we will include certain important features in our model and we will represent these important features through mathematics. So, the system could be linear or non-linear. Linear systems, they are very simple and quick to solve, but non-linear system, they represent the complexity and certain features that are also important in certain conditions. So, in order to have the mathematical modeling, we can't directly reach to a complex model, but it is better that we first develop a basic model, a simple model, and then we get some ideas of the response of that system. Then we introduce the level of complexity. We increase the degrees of freedom, we include the more specific elements. For example, here we can see that we have one forging hammer. So, this is the hammer that is falling on an anvil. So, anvil is a steel block on which the metal is kept and the hammer is coming from the top to shape it. Moreover, to stop the vibrations or impact, the effect of impact to go to the foundation, there are elastic pads that stop that work as the dissipation device. They dissipate the vibrations. So, we can now we have to develop, if we have to develop a model, we can in a first stage we can develop a very simple model. Like you can see the first model, very simple, it is a single degree of freedom model. So, here we include one mass element. So, one mass element, it contains the mass of anvil, the frame, the foundation block, as well as if there is some mass of elastic pad. Our mass of elastic pad is very less in compared to others, so it could be neglected or it could be included. So, all the mass is just one element, and then here we take the damping of soil and the stiffness of soil. In this case we have not considered the damping of elastic pad or other elements. So, this is our first model, basic model. Now, we can solve this, we can find some results, then we can improve, we can refine this model. So, in refining process, we may include the features of some certain other components of this system. For example, we can see the second figure, second model, that is the 2 degree of freedom system model. And in this we have separated the anvil, and of course this also include the mass of frame also, this anvil and frame mass, and the damping of elastic pad, because elastic pad works as a damper, it stops the vibration to go to the foundation block. So, to reduce the vibrations transmitted to the foundation block, so we use the damping of the elastic pad as an element, and then stiffness or spring constant of the elastic pad. Then here is foundation block, and then damping soil and stiffness of soil. So, here we have refined our model. This model is more complex than the earlier one. The first one is very simple, single degree of freedom system. It is easier to solve and relative to the 2 degree of freedom system. So, this is how we increase the complexity into the model. Then we have mathematical model. We have represented our system in terms of basic mass, damper and stiffness elements. Now, the next step is derivation of governing equations. So, any discrete system can be represented as a differential equations. We have to represent it as a differential equations, but before that we have to make the free body diagram of each component. So, free body diagram of each component, we have to isolate that particular component, we have to show the external force, reaction force and inertia forces on that component, and then applying certain laws like Newton's laws of motion or D'Alembert principle or energy method, we can solve that, we can develop the differential equations. So, here we have to make the free body diagram from that for each mass, each degree of freedom system, and we can write the differential equations. For a continuous system, we use the partial differential equations. However, for discrete systems, we write the ordinary differential equations. Then we go for the solution of the equations. So, the equations, they are differential equations, they must be solved in order to get the response of the system. So, response means the velocity, the displacement and acceleration varying with time. So, this response, to solve these differential equations, we have certain standard methods. We can use the theory of solving the differential equations. We can use the Laplace transform, we can use some matrix method or numerical methods. If we have numerical methods, it is easier to apply the numerical methods by using the computers. So, in case of nonlinear systems, numerical methods are more helpful because of the added complexity in the system. So, using these methods and numerical methods, we can solve our differential equations, and then we get the results. So, results, as I said, is in the form of the response of the system. It could be displacement response, displacement time plot, velocity time plot or acceleration time plot. From these responses, we have to interpret the results, means we came from physical system to a mathematical system, we worked with the mathematical system, we solved that mathematical system, we got certain results. Now, that results we have to go back to the take back to the physical system, we have to correlate these things, because our objective was to understand the physical system. The mathematical system was one middle step that helped us to understand this. So, what was our objective, what was that purpose, we want to know that, and so we from that solutions we have to make relation with the physical system. We have to know whether we want to change certain design, then what is the value of that. So, we must have the clear view of the interpretation of the results. So, here there is an example of mathematical model of motorcycle with a rider. So, here is a motorcycle and there is a rider on a road, and suppose we have to develop a mathematical model. So, we have it is said, of course, the rider is a human person. It has the mass, it has the stiffness because it has bones that work as a stiffeners, and the damping because we have these muscles, they have some damping property, they can damp out the vibration. Moreover, the motorcycle has its own mass and it has certain damper in the strut. So, there is damper and of course some spring. So, there is some stiffness and damping in the strut. Moreover, wheel has its own mass and tire has its own stiffness. So, these are, we have to, when we make the model, so we feature out that these are the components that certain basic elements we have to add. So, here we have the models. So, very first model, a single degree of freedom system. So, here we put M equivalent, so equivalent mass of the system, that is rider plus vehicle and wheel. So, we have the mass of these components. Then stiffness and damping, equivalent stiffness and damping. So equivalent stiffness could be of tire, of strut and of rider. So it is a combination of these three. Then equivalent damping could be could include the damping of the rider and the damping of the strut. Sorry. So the second model, which is we have made taking more masses and more damping, more stiffness, like we have separated the wheel mass. So we have a mass of wheel and we separated, and the stiffness as tire. So stiffness tire is connected with wheel. So we have kT stiffness and mass is then connected to the vehicle, so other body, rest of the body and the rider. So here strut has the stiffness and damping. So its strut's stiffness and damping is given, these elements, from both the wheels. So here this coming, and this is the mass of the rest vehicle and the rider. So this model has of course 2 degree, or we can say 3 degrees of freedom. If we assume these M as symmetric and everything is symmetric, then it may have only the similar characteristic, both masses may have similar behavior. Now we can even add more complexity. So we, in adding more complexity to this model, we can separate out the rider. So here we have tire, wheel, the strut, then mass of the vehicle, and because rider is sitting on the vehicle, we can take rider as separate, and this mass of rider, stiffness as rider and damping of rider. So we have added more this complexity to the model, and the degree of freedom we have increased, and of course here we will get in this case the separate responses of each component, like we can get the response of the rider, the response of the vehicle, response of the wheel. So more insight this model will provide, but the computationally it is more time taking model. Now we will discuss some basic elements, like for a vibration modeling, mass, stiffness and damping, they are the 3 basic elements. They have their certain roles. For example, we have the stiffness or springs property. They are the energy storing elements. During the vibration of the system, they store the energy when it is more, and as a potential energy, and they can give back that energy for the motion of the for the vibration of the mass. So we assume that the stiffness element has negligible mass and damping. It is pure stiffness member. It doesn't has, it is massless and it has no any damping. So of course a mechanical system, any mechanical system like beams, like bars, cables, they all have the spring property, they have stiffness property. So spring property means if we apply certain loads, they will deform, and so if we have certain bar, certain beam, we apply the load, there is the deflection of those elements, and so they have certain stiffness. That stiffness we represent as K equal to F by X, or force equal to, if we apply force F and so F equal to K times X, where K is spring constant or spring rate or stiffness. So we can see here that if we have this F and this X, and we have this spring, linear spring, so we have this K and this slope, that is K. So here we can have K equal to delta F by delta X, or equal to dF by dx, or F equal to F by X if it is linear. So here F equal to K times X. Now how much energy is stored in the spring element? So we can see here, if we have this X, so let us say this element, and this is dx. So we have energy is the area, and we have this area, so F into dx. So if it is dx, this is F, so F into dx. Now we integrate this area from, let us say, 0 to x. So this is the work done. So F equal to kx, so we can write kx into dx, 0 to x, so equal to k into x square by 2, 0 to x, that is kx square by 2, so equal to half kx square. So this is W, that is energy. So this is work done on the spring, and same energy is stored here, that is half kx square. Now we can take certain examples. For example, there is a rod. So this is a rod that has length L, area of cross section A, elasticity E, and some force P is applied, and there is some deformation, let us say delta. So delta equal to epsilon into L, and epsilon is sigma upon E into L. Sigma is force upon area, so P upon A upon E into L, so equal to P L by A E. Now the stiffness of the bar K equal to force upon deflection. So we can write P upon delta, so it is AE by L. So here we can see that the stiffness K equal to AE upon L. So stiffness is property of A, that is section, E, that is material, because it is the material properties, and L, that is the size, so length. So stiffness depends on the material, the section, the size, all these factors of this bar. Similarly, we can find out some stiffness of cantilever beam, and we assume that this is a cantilever beam, where at the end there is the mass, concentrated mass, and this has no, this beam is massless, and the mass is only concentrated at the end. So here there is certain weight W, that is m into g. We know that if there is some force applied at the end, so deflection delta, that is delta equal to force into LQ by 3 EI, and so K equal to W by delta force upon deflection. So it is 3 EI by LQ. Again here we see that the stiffness K is function of E, I and L. So E is material, I is section, it is section properties, this is representing the size. So stiffness is depending on this factor. Now spring combinations. So these spring elements can have some combinations. So they can be either in series or in parallel. We can develop the equivalent relation, that if we have a series combination, what will be the equivalent stiffness. So let's have the series combination. So springs in series, springs in series. So springs in series, we have, let's say we have these two springs in series, and they have their stiffness K1 and K2. Now we applied certain force W, and so they have certain elongation. So let's say this is delta. So this delta, let's say in each spring there is delta 1 is the deflection of first spring, delta 2 is deflection of the second spring, so the total delta equal to delta 1 plus delta 2, because the net deflection will be the deflection sum of the two deflections, because the deflection in this and deflection in this will be total deflection that has occurred here. Now we can write that now we have our equivalent this spring, and if we apply W and this is K equivalent, this much give the same deflection. So delta equal to W by K equivalent. So this spring, it is equivalent if it gives the same deflection under the end force. It means the internal doesn't matter, internal is same, means if I apply the same force W, I get the same deflection from this spring. So the relation delta equal to W by K equivalent is true for this. Now delta equal to, we can write delta and we can also write delta 1 equal to W by K1 and delta 2 by W by K2, because the same force W is acting, because they are in series, the same force W is acting on each spring. So we can write, so here delta equal to delta 1 plus delta 2, we write delta equal to W by K equivalent and delta 1 equal to W by K1 and delta 2 is W by K2. So we can write that 1 upon K equivalent equal to 1 by K1 plus 1 by K2. So this is the relation that you can see here if they are in series, that so the reciprocal of the equivalent is equal to reciprocal of the stiffnesses of the spring. So here a general expression we can write equal to sigma 1 by Ki for I equal to 1 to n if we have n springs. Similarly, springs in parallel, springs in parallel. So springs in parallel, we have these two springs. So let's represent like this. So we have this K1 and K2, and we have, there is some force W, and we find that they have been deflected. So they have been deflected. So this is K1, K2, and there is certain deflection here, delta. Now I have a equivalent spring here. So if I apply this W, so here is K equivalent, and it is giving, so it is giving, again it is deflection in delta. Now here for this equivalent we can write that W equal to delta into K equivalent. The delta will be same for both the individual spring because they are in parallel. So delta, the deflections are same. Therefore, we can write here that W1 equal to delta 1 into K1 and W2 equal to delta 2 into K2. Moreover, this W is beared by the two springs. So W equal to W1 plus W2. So here, and this is equal to delta into K1 and equal to delta into K2. So as K1 equal to as delta equal to delta 1 equal to delta 2. So W is delta into K equivalent and W1 equal to delta into K1 and it is delta into K2. So this implies that K equivalent equal to K1 plus K2. So for n springs it is sigma Ki, I equal to 1 to n. Okay, so this is the spring combinations. Now we can see the another element, that is damping element. This is energy dissipating element, because in any vibrating system there is some dissipation of the energy due to the in terms of heat or sound. So and due to this the vibration of the system decreases, the amplitude decreases until unless we are giving it some external continuous force. So this element shows that this is known as damping element, and it works based on the relative velocity between the 2 points of the system. If there is relative velocity, then it works, and the basic damper is viscous damping. So viscous damping, it is a damping that can be due to the movement of the fluid parts, liquid. If there is a piston that is moving in a fluid, so this kind of damping can come into play, and based on this we design the viscous damper. So for a viscous damper, the force velocity relation is linear. So here we can see the damper force and velocity relation. So that is linear. So F equal to Cv, where F is damping force, V is relative velocity, and C is the damping constant, and we represent this element like this. and the combination of dampers, the similar formula applies as the springs. So, therefore, if dampers are in parallel, thus equivalent will be C1 plus C2, and if dampers are in series, the equivalent will be 1 by C equivalent equal to 1 by C1 plus 1 by C2. Now, the third element and basic element is mass. Because mass is inertia element, it opposes the motion of the system, or it opposes to come to rest, or it opposes to come into motion. So, it can gain or lose, the system can gain or lose kinetic energy by this element. And in a vibrating system, there is the exchange of energy, that is spring, the potential energy, and the kinetic energy of the mass. So, this mass in the linear system can be represented with the moment of inertia in a rotational system. So, we will discuss now more on this application when we will discuss the single degree of freedom system, 2 degree of freedom system, and etc. So, we stop our lecture here. Thank you for attending this lecture, and see you in next lecture. Thank you.